In this video, let's take a look at exponential word problems. Remember, we have exponential growth and exponential decay, which are very similar formulas, but one has the plus sign and one has the minus sign. So let's write down what our variables mean for both of these. So y is our final amount for both formulas. A is the initial amount, whatever we're starting with. And then R is the rate, and the X is time. And that applies to both of those formulas. So let's take a look at some words that you might see when you come across a growth or a decay or a problem that wants you to double something. So words that go with growth are increase, increases, things like that, appreciates, and the word growth itself also comes up in problems that deal with growth. Words that go with decay, that's like decrease, decline, decay, depreciate is definitely one they use for things that depreciate or go down in value. And then we can add words to this list when we come across good ones that we find when we're working on some examples. Now, when you double something, it's a specific type of problem where you have your formula where y equals a 1 plus r to the power of x. And you want to think about, to double something, you have to have 100% of what you started with, which is the 1 that's in our formula. And then your rate would have to be double what you started with. So 100 plus 100 is what that would need to mean. So let me write this out. So y equals a. 1 represents 100% of what you started with. So that's like 100% of the initial value of a. So we'd have to add another 100%. So that means our rate is 100%. But as a decimal, so remember to put the rate as a decimal, we divide by 100. And so that's why it's just going to equal 1 when we write it right there in this formula for double. And so what ends up happening is you have y equals your initial amount, and then the 1 plus 1 would give you 2. So sometimes they skip the part where they say 1 plus 1 and they just write this formula down. But whenever that base is 2, something is being doubled. So like, think of those things that go together. Okay, so let's look at a few examples to set up for some exponential word problems. Example 1 says the number of gallons of whole milk each person in the U.S. drinks each year has decreased by 4.1% each year. In 1980, each person drank an average of 16.5 gallons of milk each year. Write an equation to model and determine the number of gallons for 2020. All right, so let's do some highlighting. It said the number of gallons of whole milk each person in the U.S. drinks each year has decreased. So decreased goes with, we wrote it up here, it goes with decay. Decrease, decay. And then we have the rate of 4.1%. That's how much it's decreasing by. And then 1980 looks like some time they're giving us, that each person drank an average of 16.5 gallons. So that looks important. And then we want to know how many gallons in 2020. So let's start to write out our model of this. So whenever they ask you for a model, we can see it's decreased. So our form is going to be decay. So y equals a 1 minus the rate to the power of x. Whenever they say to model something, you need to leave x and y for your model, because you're leaving the input and the the input and the output. You want to leave those there. All right, so what we're going to fill in is everything else first, and then we're going to answer the question, determine the number of gallons for 2020. All right, so first thing I saw was the rate was 4.1%. So let's talk about rate is 4.1%. But we have to put it as a decimal, so we always divide that by 100, and that would give us 0.041 for the rate. And then I see time was 1980 is when it started, like measuring people's average amount of milk intake. And so that means the 16.5 is your initial amount. So that's the A value. is 16.5 gallons. But then they want to know the number of gallons in 2020. So you got to think of 2020 to 1980 to 2020. Let me order them in the right way. The smallest to largest. And that is going to be the time that has passed. So from 1980 to 2020, if we need to figure that out, we can just subtract. So 2020 minus 1980 would be 40 years. So we have lots of good information. Now let's go back to this model of the equation. So we want to leave the output value of y. We want to plug in the input value, or excuse me, not the input, the initial value, the A value of 16.5 that we figured out over here. 1 minus the rate, which we figured out was 0.041. And then we want to leave room for the input value. So remember, when you model an equation or write an equation to model a situation, you always want to leave room for the output and the input. Even if you know what one of them is, you want to leave them alone. So that's the model for the situation. But then we want to also answer the question being asked. So you use the model to answer your question. So let's just scoot some of this stuff around a little bit. And we're going to rewrite our model. So y equals 16.5, 1 minus 0.041. But now we can go ahead and plug in the time of 40 years. And then let me bring up my calculator to type all that in, because we can type it now just like it looks in the calculator. So 16.5, 1 minus 0.041 to the power of 40. And we get y equals, or the amount of gallons would be 3.091. And then you can always round that off if needed. Like, it looks like it's definitely approximately 3 gallons, for example. Okay. So that's it for that one. Let's look at another example. It says, suppose the population of a city is 50,000 and growing 3% each year. Write an equation and predict the population after 25 years. All right, so let's highlight some important words here. The population is 50,000. It's growing. So remember, growing went with growth, because that's a form of that word. So they go directly together. 3% sounds like a rate. So let's highlight that. 3% each year. We want to write an equation again and predict the population after 25 years. All right. So it sounds like this is definitely growth. So let's write y equals a 1 plus the rate to the power of time. And remember, the model of our situation is going to still have the y value. We're going to fill in the a. We're going to fill in the rate. And it's still going to have that x value. But the other elements we need to fill in for our model or our equation. So our initial value sounded like the 50,000 that we started with. So let me scoot this over a little bit, because I need to have room to write that big number. So 50,000. And then my x. I need to move my arrow. Let me just erase that and point that over here. Okay. And then the rate. So the rate was 3%. So we just need to take the 3%, which is our rate of growth, and divide that by 100%. And we get 0.03 for the rate. So that would be the model of the situation. But now we want to fill in the time to predict the population after 25 years. So that is the x, would be 25 years. So just rewrite the formula. Y equals 50,000, 1 plus 0.03, and then 25 is the time. And then let's just type that in the calculator. All right. So let me zoom in a little. So I'm going to type in 50,000, 1 plus 0.03 to the power of 25. And I get 104,688.89. So let's round up to 9, because we're talking about people. And so it makes sense to round up to the next whole number for people. Okay. So let's look at another one. It says, suppose 20 rabbits are taken to an island. The rabbit population doubles every year. How many rabbits would be on the island after 3 years? Okay, so it sounds like it is doubling, which is definitely going to be growth. So y equals a 1 plus the rate to the power of time. And doubles is a very specific example. And remember when we talked about it a minute ago, that it's always 1 plus a rate of 100%, which is always like 1 plus 1. So you have a base of 2. So we could go ahead and put that, since this is one of those times that it's doubling. It's going to have a base of 2. So we just need the initial amount, which was the 20 rabbits. So that would go there. And then so y would equal the 20 rabbits, which were initially there, 1 plus a rate of 100%. So rate was equal to 100%, but when divided by 100%, that was just equal to 1. So in case you need that step in between, I'm going to write that too, because that was y equals the 20 initial rabbits, and it was the 1 plus a rate of 100%, which ended up being 1. And then that just combines to give you the 2. And then it said how many rabbits will be on the island after 3 years. So we can take our model of the situation and we can just plug in the time is 3 years. So y equals 20. We have a base of 2. And then our x value was just equal to 3. So we're going to plug that in and then just type that into the calculator. So 20 and then 2 to the third power. So we have 160 rabbits approximately. All right. So that is it for a few examples of exponential word problems.